Introduction to Sorting Algorithm. Sorting algorithms are fundamental building blocks in computer science, playing a crucial role in organizing and managing data efficiently. They are used in a vast array of applications, from searching and retrieving information to analyzing and processing data. The core idea behind sorting algorithms is to arrange data in a specific order, typically ascending or descending, based on a defined criterion. This organized structure makes it easier to search for specific data, analyze patterns, and perform other data-related operations. The choice of sorting algorithm depends on factors such as the size of the dataset, the specific order desired, and the computational resources available. In the following sections, we will delve into the fascinating world of sorting algorithms, exploring their core principles, implementation techniques, and practical applications. Fundamentals of sorting. 1. Key concepts. Sorting algorithms are based on several fundamental concepts, including comparison, determining the relative order of two data elements; swapping, exchanging the positions of two data elements within the dataset; partitioning, dividing the data set into smaller subsets based on a specific criterion. 2. Types of sorts. Sorting algorithms can be classified into different categories based on their approach. Some common types include comparison sorts. These rely on pairwise comparisons between elements. Non-comparison sorts. These use alternative methods to achieve the desired order. 3. Efficiency and complexity. The efficiency of a sorting algorithm is measured by its time complexity, which describes how the execution time grows with the input size. Common complexity measures include O(n log n) for efficient algorithms, e.g. merge, sort, quicksort; O(n) for less efficient algorithms, a.g. bubble sort, selection sort. 4. Stability. A sorting algorithm is considered stable if it preserves the relative order of elements with equal values. Stability is important in certain applications where preserving the original order is critical. Understanding exchange sort, bubble sort. 1. Step 1. Initialization. The algorithm begins by iterating through the unsorted data, comparing adjacent elements. If they are in the incorrect order, they are swapped. 2. Step 2. Iteration and comparison. The algorithm continues iterating through the data, repeatedly comparing and swapping adjacent elements. This process is performed until the largest element bubbles up to the end of the list. 3. Step 3. Repetition and sorting. The process is repeated for the remaining unsorted portion of the list, gradually moving the larger elements toward the end, resulting in a sorted list. Advantages of exchange sort. Simplicity bubble sort is known for its simplicity and ease of understanding. Its straightforward approach of comparing and swapping adjacent elements makes it relatively intuitive to grasp. In place sorting, exchange sort operates directly on the original dataset, requiring minimal additional memory. This makes it a suitable option for scenarios where memory resources are limited. Stability. Exchange sort is a stable sorting algorithm, meaning it preserves the relative order of elements with equal values. This is important in applications where maintaining the original order is essential. Disadvantages of exchange sort. Time complexity. Exchange sort has a time complexity of OEUN, meaning the execution time grows quadratically with the size of the dataset. This makes it inefficient for sorting large datasets. Inefficiency for large datasets. Due to its quadratic time complexity, exchange sort can be extremely slow for large datasets. For practical applications, it is generally not the best choice for sorting large amounts of data. Limited practical applications. The relatively high time complexity and inefficiency for large datasets limit the practical applications of exchange sort. It is often outperformed by more efficient sorting algorithms in most real-world use cases. Applications of exchange sort. 1. Sorting small datasets. For very small datasets, bubble sort's simplicity and ease of implementation make it a viable option. It can be used for quickly sorting a small number of elements. 2. Educational purposes. Bubble sort is often used as a teaching tool to introduce students to basic sorting concepts and algorithms. Its simplicity makes it easier to understand and visualize the sorting process. 3. Specialized application. In some niche applications where the size of the data is very small and stability is crucial, bubble sort can be a suitable choice. Implementing. Exchange sort in C. Include void bubble sort, int r, int n. For int I equals 0, I n 1, I plus plus. For int j equals 0, j n I 1, j plus plus. If rjr j plus 1, rj equals rj plus 1 equals rj equals rj plus 1 / swap using XOR. Int main. Inr equals 64, 34, 25, 12, 22, 11, 90. Int n equals size of r / size of r0. Bubble sort rn. For int I equals 0, in, I plus plus. Print %d ri. Return 0. Comparison to other sorting. Techniques. Merge sort. Merge sort has a time complexity of ONN. Log n, making it more efficient than exchange sort, particularly for large data sets. It uses a divide and conquer approach to recursively split the data into smaller subarrays, sort them, and then merge them back together. Quick sort. Quick sort is another efficient sorting algorithm with a time complexity of ONN. Log n in the average case. It uses a pivot element to partition the data into two subarrays, recursively sorting the sub-arrays and then combining them. Insertion sort. Insertion sort has a time complexity of O new 2 in the worst case, but can be more efficient than exchange sort for nearly sorted data. It works by iterating through the data, inserting each element into its correct position within the sorted portion of the list. Conclusion and key takeaways. In conclusion, exchange sort, while simple and straightforward, is not the most efficient sorting algorithm for most practical applications. Its quadratic time complexity makes it inefficient for large datasets. However, it serves as a valuable learning tool and can be useful for sorting small datasets or in specialized scenarios where stability is crucial. 4. Most real-world scenarios, more efficient sorting algorithms like merge sort, quick sort, and insertion sort are preferable. The choice of sorting algorithm should be based on factors such as the size of the dataset, the specific order desired, and the available computational resources.